Here's another example. So all I've done is change the coefficients, and now if you write it in this sort of packaged format, then the differential equation looks like this. The coefficients are 1, 2, 2, 4. So this is that stupid matrix that I wrote down last time just to show you an example of a non-trivial null space. And to get a non-trivial null space, you need the columns to be linearly dependent. And here I've just rigged that by making the second column be twice the first column. So I just took I just chose these numbers somewhat randomly, 1, 2, and then I doubled it to choose this column. So now definitely the determinant of this matrix is 0, right? And that means there are going to be more equilibrium solutions than just x equals 0. So what are the equilibrium solutions? Well, they're all the constant solutions that whose constant value that they take is just something in the null space of this matrix. So this is the same as asking, what are the points in the null space of this matrix? Now, we've discussed how to find the points in the null space of the matrix. You can use whatever method you want. I'm just going to look at the equation x plus 2y equals 0. There's another equation. So this is an equation solving for x star, y star, right? Looking for critical points. So there's another equation, 2x star plus 4y star equals 0. But since I'm looking at a singular matrix, there's a redundancy, right? So I don't need all the equations. If I take just one equation, that's sufficient. Okay, so that's because it's a 2x2 system. Okay, let me try to phrase that a little bit better. Since I know this is a singular matrix, it has determinant 0, I know that there's some redundancy in these equations. In the two equations, when I write x plus 2y equals 0 and 2x plus 4y equals 0, there's some redundancy. There's only two equations, so the redundancy must be that I only need one of them. And as long as I pick an equation that isn't the 0 equation, that's good. Or just stare at these and notice that the second equation is twice the first, and so it does not add any more information. Alright, so anything solving just this one equation alone is going to give us a critical point. So let me just solve in the same way I did in the previous lecture and use one of the variables as sort of a free parameter, y star here. Y star can be anything, and as long as x star is negative 2 times that thing, I am looking at a critical point. So how about I write it like this? Y star times this vector. And instead of calling the free parameter y star, how about I call it alpha or something that sounds like a scalar coefficient. Then this is, for different values of alpha, this is what all the critical points look like. There's an infinite family of them, right? You can choose any alpha you want here. There's a whole line of critical points. So here's my answer, is that x star y star equals this is a critical point for any alpha, for any choice of real number alpha. So here's an equilibrium solution, x of t, y of t equals just this constant, no time involved on the right-hand side. So there are many equilibrium solutions. Okay, let's go see how this plays out actually. So I've got my I've got my same file here from last time. So let me go and change the differential equation from what we were looking at last time. So now it's just got a 2 here, then 2x plus 4y. So I'm just writing this differential equation down, and it's the same update rule, right? Like new x equals old x plus rate of change of x times the time step. It's just the rate of change of x is now given by a different differential equation. All right, I'm going to use the same. How about? So I guess what would be interesting is if I picked my initial conditions to be on this line of equilibria. So how about I choose alpha equals 1 and I pick negative 2 and then 1 there. So negative 2 and then 1. And this is sort of just a check that the code is working. What should happen is that I get a dot at -2, 1, and it just stays there. Okay, so remember, this is a picture that just shows you a whole bunch of dots, one for each frame of the animation. And I'm only seeing one dot here, but maybe there's still an error and actually all the other dots are just off range. So then it helps to look at the animation. Let's see. Ah, beautiful. So the dot just sits there and does nothing, exactly as it's supposed to. Let's look at the actual list of points. So remember, this is time, and then this is the xy pair, and then this is the next time, and then this is the next xy pair. So you get -2, 1 always. You see? That's what we mean when we say that's an equilibrium solution. So -2, 1 times any scalar is going to be an equilibrium solution. So I could also put, let's do alpha equals 1/2. If I do alpha equals 1/2, then this is -1, this is 1/2. So then it's just that, and I have the dot starting in a different place, but it just sits there forever. So I've got this whole line here. There's a whole line here of points where if you start there, then you stay there. Let's make things a little bit interesting and try something that's not actually an equilibrium solution. So how about 1, 1? Let's see what happens. So that definitely does some movement, and it just shoots off like that pretty quickly. Now, how about instead of 1, 1, I choose something close to this line? In fact, it'd be nice if you could see the line, wouldn't it? Let me see if I can include the line here. So I'm adding to this show, which is a list of things that I want to show. I'm going to include in the list a plot of that line. Now, what would that line actually look like? So it's going to be the line of, it's going to be this line, right? So I guess I could do a parametric plot. That's probably the easiest way to do it. Alpha times -2. That's not alpha. Alpha times -2. And just alpha. And we'll let it run from alpha equals -1 to 1. Okay, there. Now you can see that line. I could also, instead of doing a parametric plot, I could just do a plot of like the function y equals -1/2 x. Right, that's kind of what that line would be. That would be fine too. So yeah, how about I start this initial condition a little bit closer to the line? So I don't know, maybe, well we already saw if I do -1 and then 1/2, then that starts right on the line. How about I start a little bit above that point? So y equals 1/2 plus 0.2. Yeah, see, now it starts here, and it still shoots away. Okay, what if I start really close? Okay, 0, 1. Just slightly above the line. Then it starts here, and it very slowly makes its way, right? And eventually accelerates. So, kind of interesting. I wonder if I start below the line, then will I shoot off in the other direction? Yep. Okay, so the point is, you've got this whole line of points where if a solution is starting on a point at a point on that line, then it'll stay at that point. So every point on here is an equilibrium solution. Now, sometimes people will draw this line and be like, these are all equilibria. Don't misread this and think that people are saying like, oh, this is a solution trajectory. It's not like you have a solution moving along this line. It's easy to misinterpret it that way. No, it's not saying that. It's saying any solution that starts on this line stays where it is. It does not actually move around along the line. It's a line of no movement.